Dear students, so today we are going to start discussing about strain energy, because the very first part of the module 3 talks about strain energy method. So unless we know what strain energy is, it will be hard for us to understand the concept of strain energy methods. So let's see what strain energy is. Okay. So you might be familiar about it because in second module you have gone through this. So the best example you might be remembering is that if I'm having a rubber band and if I'm stretching it out, okay, the moment when I release it, it goes back to its original position. Okay. So when I'm pulling it out, I'm doing some work. Okay, whatever work I'm doing, and when I'm releasing it, it is going back. So there should be some energy that is getting stored in the rubber band, which helps it to go back to its original position. Okay, so the work done is getting stored inside. So the energy that is getting stored inside by straining a material. Okay, when a material is getting strained, the energy that gets stored inside the material is called as strain energy. Okay, so strain energy is a type of energy that is getting stored, and we can see that the strain energy, normally represented by U, is equal to the work done. Work done is force times distance, right? Force times distance is the work done. So we know that strain energy is equal to the work done. Okay, I took a rubber band, I pulled it, so I did some work, which means I applied a force and it got stretched by certain length. Okay, let it got stretched by a length d when I applied a force P. So the work done will be P times delta, where delta is the stretched amount, the length stretch, and P is the applied force. But you may be remembering this equation of strain energy not as P delta but as half P delta. Okay, where this half came into the picture. So this is basically from, you might have got introduced it by showing a graph like this. Okay, and in here you were having the deflection values delta, and in here the load or force values P, and you might have got a graph like this, and if this is delta, this particular value is P, this area is called as strain energy, which is half P delta. That's what you might be remembering. So why we are considering only this area and ignoring this? So that is the first thing that you should understand. When we talk about strain energy, we are taking the case of a gradually applied load. So I was having this rubber band. Okay, I applied a zero force. Then I'm gradually applying the load. Okay, I'm not applying a load suddenly. I'm applying a load gradually, which means that in the initial condition, the force applied is zero. When the force applied was zero, the displacement was zero. When I applied the maximum force, which is a gradual application from zero to the maximum value, I was getting a maximum displacement delta. So basically what we are considering here is the average force exerted. Okay, from 0 to P, so average force is half P, and the half P into delta is given as the work done. Okay, so this is what the parameter strain energy is, which is normally represented by capital U, and it is half P delta. And you have reformed this particular equation by substituting the value of delta in terms of P and all those things you might have done. So we know that from engineering mechanics, not from engineering mechanics, from mechanics of solids, you might have learned that if you are having a rod and it is subjected to a force, say P, a tensile force P, the deflection that will be happening for this bar, okay, the deflection delta, for example, because of the application of the force, it got elongated by this much amount. So this amount I'm calling it as, say, delta, that is the deflection or the elongation happened due to the applied force P. If the cross-sectional area, okay, cross-sectional area is A, the length, the initial length is L, and the Young's modulus is E. Okay, that is a material property. This is a cross-sectional property. And if we know these parameters, we might be familiar with the equation that in this case, the value of delta is given by PL by AE. Okay, a very simple expression that you will be remembering from mechanics of solids. And this expression also, if you want to know where it came from, is a very simple derivation. We'll talk that in a few minutes, just 1 or 2 minutes will take. We'll have that deviation also. This expression, you can see that we have the basic Hooke's law. Hooke's law states that stress is proportional to strain, or stress equal to Young's modulus times strain, right? Stress is basically force by area, and strain is change in length by original length. So when you reform this equation, what will you get? Delta is equal to L will go to the numerator, E will go to the denominator, and what we basically get is the expression for change in length delta, which is PL by A. Okay. So once you have this value, then you can substitute it back in here. So you'll be getting U is equal to half P into PL by AE, that is P square L by 2AE, which we call it as strain energy. And similarly, you might have already, you're familiar with the term strain energy density. Okay. So here we calculated the strain energy using the P delta curve, that is force displacement curve. Instead of force displacement curve, if you're plotting the stress strain curve, okay, if you're plotting the stress strain curve, and if you're considering the area here, which is basically half sigma epsilon, this parameter is called as strain energy density, or normally represented using the small letter U. Okay, strain energy density. Okay, we know that if we talk about density, it is basically mass by volume, or weight by volume. So here when we talk about strain energy density, it is basically strain energy by volume. Okay, we have the expression for strain energy, which is half P delta divided by volume. What is volume? What will be the volume of this particular bar? If the cross-sectional area is A, length is L, we know that volume will be A into L. Okay, A times L. Now if I try to reform this equation will be half into this P by A. Okay, you can club this term P by A, and we know that P by A is force by area, which is stress, and delta L by L, that is change in length by original length, which is our strain. So you can see that the strain energy density is equal to strain energy per unit volume, which is equal to half of sigma epsilon. So these are the different conditions we consider when we talk about strain energy. Then similarly, you might have heard about resilience. Okay, all those things that you have learned those things in detail in module 2, but this is the basic thing that we require for module 3. So this is the case when for a rod which is, or a bar which is subjected to an axial load. So this strain energy expression, that is, I'm writing here, that is U equal to P square L by 2AE is the strain energy for a axially loaded member. Okay, for an axially loaded member, strain energy is given by P square L by 2AE. Similarly, for a member that is subjected to a bending moment, okay, that derivation part you can see in your notebook. In module 2 you will be having that. Just refer back to your notebook and you are going to find the expression for member subjected to bending moment. The strain energy expression is given by integral m square dx by 2EI. Okay. So these are the two expressions that is highly needed when we are going to deal with the problems in module 3. Okay, so that's the basic concept of strain energy and how we got these two expressions. So now we are moving on, and let's see what Castigliano did. Okay, the Castigliano's theorems are what we normally use to solve for deflection using strain energy method. So what did Castigliano do? He proposed two theorems. Okay, and if you think closely, the two theorems, even if he is not proposing, you could have proposed it pretty easily. Okay, what were the two theories? So we know that strain energy is the work done. So in general, I can say that U is proportional to P times delta. Strain energy is proportional to load times deflection. Okay, so what Castigliano did is he just used this expression and created two theorems. Okay, so what is first theorem? Theorem 1. Okay, theorem 1 and theorem 2. In theorem 1, what he did is he said that delta is equal to U by P. In theorem 2, he said that P equal to U by delta. Okay, isn't it obvious? We all know when U can be written as P into delta, delta equal to U by P, or P equal to U by delta. It's clearly visible. But he didn't put it like this. He used a complicated sentence by introducing the concept of partial derivatives and all those stuff. And do you remember the expression? The expression says that the theorem states that if the strain energy can be represented as a function of forces, okay, that is, if you can represent the strain energy as a function of forces, then the deflection at any point is given by the partial derivative of strain energy with respect to the corresponding load. Okay, delta equal to dou U by dou P. And in theorem 2, what he said that if strain energy can be expressed as a function of deflections or displacements, then the load at any point is equal to the partial derivative of strain energy with respect to the corresponding displacement. Very simple. These are the two theorems proposed by Castigliano. And this first theorem is what we are using for deriving the basic method that you already know, which is called as the unit load method. Okay, so we can see how we can arrive from this equation to something which is highly useful for us to solve the problems. So I'm considering this part. Okay, this part I'm considering. So here what I'm doing is I have the expression deflection at any given point is equal to partial derivative of strain energy with respect to the load at the corresponding point. Okay, say I'm putting delta I is equal to dou U by dou Pi, because delta and load, that is the deflection and the load, should be at the same point. Then only this particular theorem will be valid. Okay, so I'm trying to rewrite this equation. So we have the expression of strain energy as integral m squared dx by 2EI. I'm considering the case of strain energy due to bending moment, because when we talk about beams, we talk about flexural loads or bending moments. When we are talking about axially loaded member or truss, we may be speaking about integral or summation of P square L by 2AE. Now we are talking about beams, so this is the particular expression that we are interested in. So strain energy is integral m squared dx by 2EI. Now I want to do this particular operation. Okay, I want to differentiate U, partial differentiation of U with respect to dou Pi. So how will this get modified? So when I do that, I can take the integral outside. Now m square, partial differential of m square with respect to Pi is going to be 2m times dou m by dou pi. Okay, this is basic mathematics. When you are differentiating with respect to pi, this m square, it becomes 2m times dou m by dou pi dx divided by 2ei. Okay, this is basically the deflection delta I. Okay, here the common terms will go away, and finally this you can just eliminate this numerator and denominator, and finally what we are having is an expression integral m times dou m by dou pi dx by ei will give you the deflection. This is the important formula that we need if we want to solve problems using strain energy method for analyzing indeterminate structures. So this is the very fundamental equation that you should be knowing with great depth. Okay, so we have seen the step-by-step way of deriving this equation, because the problem is that there are a lot of parameters or variables involved in this equation that at the time of exam you may tend to forget it. So if you are not getting the proper equation in the by heart way, so what you can do is you can go for the derivation way. So you need to have the expression for strain energy, then you just need to use the Castigliano's first theorem, that is dou u by dou p. When you partially differentiate this strain energy with respect to dou pi or with respect to pi, you are going to get this expression. Okay, this same thing is what got converted to the so-called unit load method. Okay, the unit load method. In unit load method, there is a simple equation that you may be remembering, that is delta or theta. When I say delta, this delta represents displacement. Okay, this displacement can be a deflection or a rotation. Okay, you should never forget that. It can be either a deflection or it can be a rotation. So delta or theta is given by integral mm dx by ei. This is the equation that we use when we are dealing with the problems of calculation of deflections using unit load method. So you can see that here we are having a value m. Okay, if you can see here in this equation, if I am replacing dou m by dou pi by m, these two equations are same, right? Both the equation, this expression and this expression are same. Okay, and do you remember what m is? Okay, what m is? Capital M is the moment due to external load, and small m is the moment due to unit load. Okay, so this is the basic concept, and I know that you may be finding it hard to grasp this equation as such, but don't worry, we'll try to do problems using this equation also, so you will clearly know what capital M means, what small m means. Okay, and here also what is capital M, what is EI, and what is EI? EI is the parameter called as flexural rigidity. Okay, flexural rigidity. Okay, flexural rigidity basically means that the rigidity of a material against flexure or bending. Rigidity is basically kind of a resistance or a stiffness, right? If you are trying to bend something, it will say if I am trying to bend a steel rod, it shows some resistance. That resistance can be termed as rigidity. Okay, so the resistance or rigidity against bending is called as flexural rigidity, which is given as EI. Similarly, in the earlier case we were talking about a rod that is subjected to an axial load, right? So I'm just using this. So we have considered a case where a rod was subjected to an axial load. So when I apply a tensile load, it resists the elongation. I need to apply a lot of load so that it will get elongated. So there also I am getting some resistance or rigidity. So when it is a rod which is subjected to axial load, the rigidity is called as axial rigidity. Okay, and axial rigidity is given by AE. Okay, this AE is called as axial rigidity. Okay, so axial rigidity is AE and flexural rigidity is EI. Okay, so both you are going to find E. What is E? E is basically a material property, or we can call it as the Young's modulus. So when I consider this this sketch pen, okay, I am applying a force, say a force of amount 10 Newton. So I'm going to get some elongation. But instead of this, if I'm using a steel rod having same diameter and same length, and if I'm applying the same force 10 Newton, I'm going to get a totally different elongation. Okay, this may elongate, but the iron rod, by applying 10 Newton, it's not going to get much of elongation which is visible to the common eye or the naked eye. Okay, so what changed in these two cases are, the first case, let this be the sketch pen and this be the iron rod. So when it was the sketch pen, the E value is something else. When it is iron rod, the E value is different. So we know that the rigidity or the resistance against deformation depends upon the material. Okay, that's why the E is there in the picture. So E is there. In case of axial case, the next one is A, which means the cross section. If I'm using this sketch, instead of that, if I'm using a sketch having larger diameter, okay, when it is a larger diameter sketch and I am again trying to pull it, so then what happens is that the sketch pen will be showing different values of deformation. This will be deforming to one particular value. The one which is having higher diameter will be deforming to some other value. So the cross-sectional area plays a picture. So that's why in case of rigidity or the resistance against deformation for an axially loaded member, the two parameters involved are, one is the cross-sectional area, other one is the Young's modulus, such that axial rigidity is given by AE. And when we are talking about bending, okay, when we are trying to bend something, the thing that comes into the picture, it's not the cross-sectional area, but it will be the moment of inertia. Okay, we are very familiar with moment of inertia. Okay, when say if I'm having a scale like this, and if I'm applying a force, when I'm placing the scale like this, it easily bends. Okay, the bending is pretty easy. But if I'm placing it like this, now it is very hard for me to bend this one. So even though I'm applying the same amount of bending moment, this one is not bending, but this profile is bending very easily. So what happened? Does the cross-sectional area changed? Does the material change? No. The only thing that changed was the orientation of the cross-sectional area. So a parameter that consider or takes into account the orientation of the cross-sectional area is the moment of inertia. Okay, so when we talk about the rigidity against bending moment, we will be considering not the cross-sectional area but moment of inertia. So the material and the moment of inertia, hence we are getting the flexural rigidity as EI and axial rigidity as AE. Okay, so we'll wind up this video right now with this very basic things, and in further lectures we will see how we can enter into the third module. Thank you.